Are we good to go?
Yeah, all good on my end.
Okay. All right. Well, welcome to this the third. I think it's the third session of VMIL, and we have four talks in this session. The first of which is, as you can see on screen, is going to be given by Meetesh Mehta. The title of the talk is Debugging Dynamic Language Features in a Multi-Tier Virtual Machine. And I'll hand over to you, Meetesh.
Thank you so much. Hi, this talk is about debugging dynamic language features in a multi-tier virtual machine. So this is our team. We are from IIT Bombay and IIT Mandi. So unfortunately, couldn't be there for the offline presentation, but here we are. So let's start off with dynamic languages in general. So dynamic languages are great. In the focus of this talk is on the R programming language, but the concepts apply to other languages as well. So people write a lot of dynamic language code, and particularly the features that I find to be the most interesting are dynamic typing. It helps us write neat and tidy code. First class functions and environments help create a nice abstraction around a lot of code that we write. And then we have some subtle features that are made by language designers, like lazy evaluation. And this is one feature which a lot of languages implement in their own way, and the places where it tries to behave lazily or not is defined by each language. And after that, we have some less common features like runtime reification of environments and access to the runtime stack. And this is a feature that I don't think many languages would support for obvious reasons, but it does come handy in R. And after all this, we have the most favorite language feature for all compiler engineers, that is eval. And yes, it makes compiling and optimizing challenging, but it does come useful in debugging. So these are dynamic languages, and running them fast has been a big challenge for a long time. And one of the common ways of speeding up these languages has been to design VMs and optimizing code on the fly. And in context of R, a paper by Olivier et al. In DLS 19 presented an IR that tried to optimize R code. And one footnote from that paper really resonates when you start working with R. So the footnote says the sound one makes upon realizing that arguments can modify the environment of the function they are given to, and such dynamic language features, even though they make writing code much easier for the end user, makes it really challenging to optimize for. So a 10K feet view for a VM to an end user is it's a black box to which a user passes a program, and somehow it speeds it up. So you have a 10x speed up, and sometimes when things don't go as well, you see a 300 times or 1000 times slowdown. And this is a problem that many VMs face, and this is something that plagues a lot of VMs in the current day. And the way these VM works are very interesting. So they do a bunch of things behind the scenes and usually not visible even to the people who are experienced in that language, and only known to the VM implementers is things like compilation, profiling, calling conventions, specializations for different contexts, and so on. And really, these are a lot of complicated integrations that do indeed bring in a lot of bugs, and which make it really difficult to debug. And not just for the maintainers of the virtual machine, but it's also difficult to find and reproduce bugs, because there'll be things like the garbage collector that sometimes eats up your memory, and this is a real problem. And so in this talk, we want to focus on three aspects of the virtual machine of our interest. And the three aspects are interpretation, profiling, and specialization. So what exactly happens when you interpret code? Because an end user writes code line by line, expecting that each statement does what it's supposed to and it gets stored somewhere in memory, but that's not really what happens behind the scenes. And profiling, what exactly does the VM profile, and is there something that the user can do to write better code? And specialization is something that many VMs do to generate code on the fly for specialized use cases. And these are the aspects that this work focuses on. So we work on the Russia virtual machine, which is an interpreter for the rear bytecode. So our tool is called Derir. So D stands for demystifying and debugging, where rear is the rear bytecode that the system interprets. So, looking at the VM view from end user perspective, like the kinds of questions that one might have is, okay, I've written, so let's consider hello. Hello. Uh, am I still connected? Okay, so I'll continue. Uh, okay, so starting back, maybe there was a brief disconnection. Yeah, so from a slightly more experienced R user, we might, who writes a lot of R code, you might, he might experience the system sometimes running fast and sometimes running slower. But what might happen is the runtime might optimize for a different specialization, and hence the code runs faster. So, and one of the last feature that language designers are interested in, what happens when we try to increase the expressive power of the system. Let's take this piece of code for example. Let's say we have a function foo that iterates over I from 1 to 20, and when I reaches 5, it executes f of break. So what does this even break mean? How does it get interpreted? So in case of R, which supports lazy evaluation, this is indeed not evaluated and just simply gets passed to f. And when f is executing, it instead passes this argument back to G. And when we do that and assign it to a local variable inside G, it gets forced. And when this force happens and when the break is executed, it jumps and the control flows outside the for loop. So typically not anyone would write such code, but this is a valid piece of our code. And when people optimize when people try to optimize these functions, these weird things have to be accounted for. So the Russia JIT compiler takes into account all of these corner cases when optimizing code, and contextually specializes different functions. And because of this, it does experience a huge warm up and does have strange compilation behavior sometimes. And in order to study these, there are different tools that we developed over time. And one of the first ideas that we had was to just visualize traces. So the question was, do contextually specialized functions even ever get used, or is it the case that over time only general functions remain and the specialized versions get discarded? So in this image, you can see all the colors, and all of these unique colors represent different contextual compilations for functions. And as time progresses, we see that a lot of these different colors emerge, and they are not dominated by a single color, which means a lot of these compilations are indeed useful in the system. Apart from studying traces, one might also consider looking at call graphs to understand how the specialization behavior works. So in this image, there are two root nodes, that's the execute on the left and one execute on the right. The execute on the left is the interpreted version of execute, which does a lot of, which further calls a lot of different functions, and these are non-optimized versions of execute. Whereas on right, we see optimized versions of functions that are optimized version of execute, which reduces the call graph significantly because it just managed to inline most of these functions that get further called. And an other popular approach to debugging is event query, where you store a bunch of events, and for a problematic event, you might try to work backwards. And this was also one of the tools that we developed to help us debug certain aspects. So the point I'm trying to make here is it's just about selecting the right tool for job. There is no one size fits all solution, and uh, the tool has to be specialized for a special use case and has to show the least amount of information that is useful and it's easy to use. So this is our tool. It's called Derir. So it can load up the function on the left. So this shows the rear bytecode. The second block that's below it shows the current closure, the way it was interpreted inside the system. The third block shows the environment. Fourth one shows the stack. The fifth one is the call graph, and the sixth one is the lattice of context. So I'll switch to a small demo of how our tool works. So let's consider function f, which calls g, and g, which calls foo, and see how the runtime behaves. So the way we connect to a visualizer is using an API call in which you pass the server address as the argument, and then it simply connects to the viz. So when the program is started, the runtime pauses at a relevant event and shows all the debugging data and the data that was shared from the backend to the front end viz. and the viz, as you can see, it's on the 0th bytecode which is to be executed, and the environment already contains a and b which were passed to it, and also the stack contains the promises that were passed. So as the execution progresses, and we can see how the stack updates and the function is pushed on the stack, followed by the promise being pushed on the stack. And when we step into the call, we see the call graph update, and more things emerge on the stack as we continue with our computation. So at this point, when we are executing bytecode offset 7, you see it says load var cached A, that is simply the argument A. And if we look at the environment, that it's an promise which is not yet evaluated. So now when we try to step through, we will end up inside the promise, and we would evaluate it at this point. So as we continue evaluating, we see that different feedback slots also get populated. And so let's just restart the execution from this point on to show you how we can modify the runtime state to see different aspects of the system. So we quickly step through to the offset that we last reached, and instead of directly executing offset 7, we will first update the environment to change it from a promise, and the binding now points to a simple integer. And now when we step through the bytecode, we would see that there is no promise to be evaluated, and the step function simply just steps through. And if we look at the feedback, we would see that state before last force flag is set to a value, which means it was never a promise, and the code sees as that it was just a value that was passed. So, evaluating such behavior is useful in context of R because promises are expensive. They require more code to be generated and maintained. And passing eager values is in general fast as a calling convention in R. So when the program exits, it simply disconnects. So let's now try to connect one more simple example. And so this is context.r, where a function foo is called or connected to the viz, and we now call it with two different kinds of contextual arguments. So the first kind of call was with two integers, and we see that the feedback slots end up storing that it's an integer, and the s denotes that it was a scalar value. And one interesting thing to notice here is the value of a and b were passed as evaluated promises, which are just values that won't have side effects in R. If we continue our execution through the second call to foo, and if we continue to the third call, we will see that a new specialized version of foo was created, and the lattice of context updates. So we are at line 13, and we can see that this call ends up compiling foo for a specialized version and will dispatch to native code. So continuing with the execution, we see that the feedback slots at 9 and 23 also get updated to denote that promises were passed. So this means that uh, vectors get passed as promises, whereas integers get passed as evaluated promises or just values in case of R. And as the execution proceeds for the second contextual call, we see one more specialized context emerges, and in this case we see even though we had a specialized context pass, the runtime decided to compile a more generalized version which will suit more context. So the runtime behavior changes from run to run because it has a lot of heuristics that decide when compilations will happen, and this is just an example of that. So continuing with my talk, so what we were able to use this tool for, so this tool was meant to be a learning tool and to discover small, simple bugs that might exist in the system. And what we found was there is an implicit return that every function generates, and when you use the keyword return, redundant return also gets generated. So this is just a small redundancy in the generated bytecode that increases bytecode size. Something more subtle is that we see the bytecode state as it progresses over time. We can see that the context, the feedback that's collected gets generalized. So the first call here was recorded as an integer scalar which was passed as an evaluated promise. Whereas in the second state, we see that the S is gone, which denotes that it can be a vector of integers instead of the smaller context that is a single scalar integer. The third image shows that a specialized version was created to handle simple integers. So these represent the predicates under which the compiled version is valid. For example, the first predicate says that there are no explicitly missing arguments. The second predicate says that the correct ordering was passed. The third predicate says that there were not too many arguments. Believe it or not, in R you can pass more arguments than expected by the function, and those get interpreted in special ways to support specialized dispatch. And then argument match, which means the arguments match the order in which they're expected. And the other predicates are simple that say that the zeroth argument is eager, it's non-reflective, it's not going to be an object. It's a simple integer, and the number of missing arguments is 0. And the final state is when we pass a different kind of an argument, we see it gets even more generalized to say that the feedback here says that it can be an integer or a logical and maybe a promise. So feedback slots are fixed size slots that appear as inline caches within rear, and they store a lot of and they store field values that were recorded at that point. And the Derir tool can be used to modify these values and see what happens in the runtime. The conclusion of this talk is that specialized tools are really useful in gaining insights, and mature frameworks like React making these tools really easy. The bad is there is no one size fits all solutions, and if you keep creating these tools for specialized problems, the documentation is really hard. So a lot of these tools that we made earlier are not maintained, and it would be good if there was a generalized framework where all of these could be fit into. So the road ahead is try to see how much of this work can be retrofit for other use cases, and an outcome of this tool or our work is being presented as at UPSLA a few days from now, which is on reusing just-in-time compiled code. So this is in context of R and will be presented by Jan. Thank you.
Any questions? Okay, we don't have any questions here at the moment, but that was a very interesting talk, and thank you for that. We shall move on then to the next talk. Thank you.